So good evening all. We can start after 2-3 minutes. We can wait for another 2-3 minutes. After that we can start. Okay, I think we can start now. Let me share the screen. Okay, I think my screen is visible to everyone. Okay, so let's start. So good evening all. So myself Suvankar Mandol from Indian Institute of Science. So I am one of the TA of Electrochemical Technology in Pollution Control. So now we are in 5th week. So most of the things, introduction and properties of solution, 2 weeks we have discussed, and last week we have discussed different type of redox chemistry, acid base titration, and potentiometric as well as conductometric titration. So today we'll discuss more about polarography and Karl Fisher's titration, some of the problems of that. So I will not go what professor have discussed, but I will discuss some of the problem, and along with that we can discuss more details about that problems and how we can proceed with that thing. Okay, So last week I think we have discussed lots of question on redox chemistry. So how we can calculate the electromotive force of a cell, and how half cell and full cell we can combine, and that can give the potential, and which one can be reduced, which one can be oxidized. So many things we have discussed. Okay, so today we'll discuss some of the key question of previous year assignment. Along with that, some of the interesting question also we have discussed. We'll discuss. Okay, so this is the first question. I think I did not give the question number, so it's okay. I can give now only. Okay, so the question is, the function of mercury in polarography is to provide a renewable electrode surface as cathode, to provide stabilization of polarographic maxima, to collect mercury in the anode, and to eliminate interfaces. So if people can write in the chat box which one will be the answer. Okay, so polarography basically we have discussed I think last class also, and this week also we have learned about the polarography. So basically you have mercury electrode, and which is working means which is acting as a working electrode, or we can say representative electrode, which can give the information about the redox reaction. So we have discussed, sorry, so we have seen that in the figure, that you have some capillary, and on the capillary you have some container which can contain the mercury, and their drop can be formed, so that is called CGME. So CGME basically control growth mercury electrode. Okay, so basically you can control the growth, whatever form what is called your mercury drop is forming, so that you can control how much time you want to fall. So that time also you can control, and you have the container. I think I can plot here because that I have written there. So I think you have that container which contain the electrolyte, and you have long capillary, along with that where you have I think so you have mercury drop. Okay, so that dropping on the your electrolyte, and it is connected with the potentiostat, and another electrode, another container. So that is if this is the cathode, that will be the anode, and that is called potentiostat. Okay, so that is there, and what is called we use mercury electrode. There is some of the advantage. So what are the advantage we have learned in the in this week, that what is called one by one I can write in the whatever we have discussed. That one is its surface is renewable. One is surface is renewable, because what is called when one drop of mercury is touched or to the electrode, some redox reaction is happening, and that is coming out from the capillary. So again new drop of mercury is reproducing. So that's why it is what is called the surface of the electrode is renewable. If you use some polarizable electrode, like nowadays people use what is called glassy carbon or platinum electrode, where with time when you are doing the reaction, that electroactive pieces or analyte is deposited on your electrode working electrode surface with time when you are doing the cycling or for long time reaction. So that means when your initial state, your working electrode is completely fresh or clean condition, when you are using for long time some analyte is depositing, so your working electrode is not completely clean. So that's why what is called that electrode is not renewable. So but in the case of mercury, that's not the case, where you are dropping new dropping electrode dropping drop is forming. So that's why the new surface area is reproducing. And other thing, other also we learn that it is reproducible. Reproducible means whatever, suppose first case you have produced one spherical drop of mercury, that is suppose 10 semi cube, and second time also if you want to make same area of or same volume of mercury, that can be produced. So that is the thing. And as it is a liquid, so the surface is smooth, because for whatever electrochemical process or theory has been developed, that is developed for smooth surface. Okay, so surface is smooth. So that is one advantage of using dropping mercury electrode. And second electrode was that it can form the amalgam. It can form the amalgam. What is the third advantage? What is the third advantage? So if diffusion current is assumed to steady value immediately after changing the potential, and it is reproducible. So it means we have observed that if you you have a current and your voltage and you are sweeping. Okay, so when there is a not enough potential where the reduction or decomposition of analyte is happen, so that potential you are not reach. But after that, when the potential, when the potential reach to the analyte decomposition, so you will get a high current. After that it is to steady state. So basically it is to like this, but actual case how is it is to happen, that you will getting the current like this. When the drop is formed and it is touched to the electrolyte, it will show the high current like this. After that, when the drop is come out from the capillary, there is a disconnection between the your potential state and electrolyte. So that's why what will happen, that your drop what is called current will be drop out suddenly. After that, when new drop of mercury will form, again it will go to the same current value. So it will be like this. Actual case it is to like this. So if you plot for steady state, so it will be it will come like this. Okay, so basically here the this is the diffusion current when your current value is happening. After that it is becoming steady state, or slowly it is to increase. Why it is slowly increase? Anyone can tell? Or why after sometime it is steady state? Anyone can unmute and can tell? So this is slightly increased, or it is steady state, and this is also steady state. Why it is steady state? Okay, so I can tell. So basically what you have, that you have a electrolyte, you have container, and you have electrolyte, and your dropping mercury electrode is forming here and touching like this. So your connection is forming and you are getting the current. So if I see that you have a electrode surface like this and your bulk electrolyte is here. So what is basically happening, that when you are potential is sweeping at particular potential, you are suppose in the solution you have Fe what is called 3 plus is there, and now in the electrolyte everywhere Fe 3 plus is there initially, and at that particular potential where Fe3 plus is going to Fe2 plus, that case that Fe3 plus is diffused to electrosurface and it is formed to Fe2 plus. Okay, so as there is a concentration gradient because at the electrode surface, okay, at the electrode surface, what is there? Fe2 plus is there because Fe3 plus is converting to Fe2 plus. So Fe3 plus is reducing to Fe2 plus. So that means in your electrode surface, Fe2 plus is there, but in the bulk electrolyte, Fe3 plus is there. So that means Fe3 plus concentration in the electrode on the electrode surface is low. So that means there is a concentration gradient. Concentration gradient. So due to concentration gradient, your current value, whatever it is increasing, so after that, this current is called diffusion current. So this current, diffusion current. Now after some time when it is reached to the this value, after that continuously your Fe3 plus is coming to your electrode surface. Okay, this electrode surface your Fe3 plus is continuously is going. So your new electrode surface is forming and Fe3 plus is continuously going to your electrode surface. So that's why it is a steady line is coming, and with time it will little bit slowly it will increase, but almost it is steady state current. So because you are continuously from the bulk solution to your electrode surface, Fe3 plus is going. Okay, so that is the thing. So I can now we can discuss what is the question. So the function of mercury in polarography is to provide a renewable electrode surface as cathode. That is true. Okay, to provide a stabilization of polarographic maxima. So polarographic maximum, as I have told, that it is what is called after in reality it is like this, but actually it is like this. Okay, so sometimes it's dropping down, so that means option B is not correct. To collect mercury in the anode, so that is not also correct, but it is called anode also can be used as a mercury electrode. So okay, but mercury is not collecting on the anode side. Okay, to eliminate the interfaces, so that is not the correct answer. So the correct answer is to provide a renewable electrode surface as a cathode. Okay, so this is the answer. Now we can go to the next problem. So in the Karl Fisher titration, end point is determined by color change, chromatographically, gravimetrically, electrochemically. So which one will be the answer? Anyone can unmute or they can write in the chat box.
A and B.
A and B, okay, by color change and electrochemically. Yeah, so that is the correct answer. So what is Karl Fisher titration? So what is the Karl Fisher reagent? I can say what is Karl Fisher reagent? Can anyone tell? What is Karl Fisher reagent? So basically, what is Karl Fisher reagent? Basically, what is which purpose is to use this Karl Fisher titration? One is to find small amount of water in any salt or solution or any medicine, etc. Okay, So basically Karl Fisher reagent, what we know that basically Karl Fisher reagent pyridine you used to take. Pyridine, this is the pyridine structure. Along with that, iodine solution you used to take along with sulfur dioxide. And in which solvent you used to take? What is the solvent name?
Alcohol.
Yeah, alcohol. Basically methanol you used to take. Okay. So basically this iodine which is oxidize the sulfur dioxide to sulfur trioxide. So this iodine, so pyridine, what it will form? C5H5 NH plus iodine when it will oxidize to sulfur dioxide to sulfur trioxide. So this one will reduce. So when it will reduce to I minus, it will form. So it can coordinate with the pyridine. And this methanol and another sulfur dioxide, when it will form sulfur trioxide because it will oxidize and it will coordinate with another pyridine molecule. So it will form C5H5 N SO2O minus. Okay. So this is happen, and what is called in general iodine. After that, what will happen? It will react with the methanol solvent. So that will it will form C5H5 N OSO2O methanol. It will be, and here hydrogen. So ultimately this is the colorless solvent. So basically what will happen, that why it is we have chosen by color change, because iodine basically in brown color it used to. Okay, so brown color, when you will add pyridine, or suppose you have taken the analyte in your electrolyte and you want basically in the solution methanol you used to take. And initially they used to take the dry methanol solvent. Okay. And first as they will take check that in the methanol is there any what is called water is there or not, because you want to check suppose some compound which has contained the water, and you want to measure the content how much amount of water is there in that compound. So that you used to do in the methanol solvent. So for that, what they used to do, that they will do first in methanol is there any solution what is called water contain or not. For that they used to take dry methanol in the container, and in that they will add the Karl Fisher reagent. So all this thing it is known as the Karl Fisher KF solution. Okay, so these things, so they will add drop wise. So initially it will be brown color. Okay, and when they will react with this and this complex will form, it will be colorless. Okay, then from the burette, as this is coming from the burette, sorry, so they used to add from the burette. So from initially how much amount of Karl Fisher reagent is there, and after adding how much Karl Fisher reagent is consumed for methanol solvent. Okay, so suppose initially it is 20 ml of Karl Fisher mark was there, and after adding Karl Fisher reagent 2 ml, suppose 18 ml it is becomes. So that means 2 ml is consumed and it's became a colorless solution. So that means 2 ml equivalent of Karl Fisher reagent water is there. So as we know that it is called Karl Fisher reagent 1 ml of KF solution, Karl Fisher solution reagent equivalent to how much water molecule? 6.66 mg of water. Okay, so these things is there means actually this solution in available in the market. So when you will do means take or buy the Karl Fisher reagent, so it is written that how much 1 ml of Karl Fisher reagent equivalent to how much of water. So usually initial state people use this pyridine reagent, but this pyridine usually it is toxic in nature. So for this nowadays people use imidazole reagent. Instead of pyridine they use imidazole. So it is almost equivalent structure. There is two nitrogen is there, two nitrogen atom is there. So imidazole it is to use, and it is equivalent 1 ml of Karl Fisher reagent for imidazole. That is around 5 mg of water. Okay, so initially they will take this dry methanol solution, how much water is there. So whatever water value water is there, that will oxidize. So iodine it will going to I minus. So due to that your water molecule fully consume whatever it is there in the methanol solution. After that you add your what is called analyte. You can take, so you add analyte. Okay, then analyte again you add this I2 it is called Karl Fisher reagent, and when again it will become brownish color as it contain the water molecule. So this thing, and these things is again it will become the colorless when the end point will reach. Okay, so that and after suppose you add the analyte, and you after that you are adding the Karl Fisher reagent, and it becomes 16 kml. So 2 ml again it is consumed. So from there you can calculate how much amount of water is there. Okay, so that is this is the color changing process. But sometimes what happen that this color change means you are manually you are observing the color change. So sometimes people will think that one drop of Karl Fisher is added, and that things means people another people have added another one drop, another drop. So that's why the value of counting of water there is some error, because we are measuring the water molecule in ppm level. Okay, so that's why it's preferred to do electrochemically. So in the solution we have the iodine, so iodine is to going redox reaction is happening, so iodine going to I minus, to I minus. So as there is redox reaction is happening, the electron transfer is happening, then you will get the what is called current value. Okay, so when you in your system you have the iodine, then you will get the current value like this. When the end point will come, it will become to zero, the current value. Okay, so with time I can write, so current value will be zero. So from when the current value will be zero, that time you can tell that it's reached to endpoint, and then you can calculate how much Karl Fisher reagent is consumed, and from there you can calculate the how much what is called reagent or means how much water molecule is there in your compound. Okay, so as I have mentioned that nowadays people using what is called imidazole reagent. So imidazole basically the analog or I can say the five-member ring of five-member ring kind of thing. So here you have the this kind of structure. So this is the structure of imidazole. So the reaction mechanism all are same, whatever we have discussed for pyridine. So in this case also this kind of complex will form like whatever NH2, and the sulfate ion, this will be positive, and sulfate ion whatever this minus and OCH3. This kind of complex is to form, and other two imidazole, because iodine is there, so that will minus. Okay, so that means here I can write iodine. So here 2 iodine, so this will be 2. Okay, so this is quite simple. Okay, now we can go to the next question. So the answer is D and A. Okay, by color change as well as by electrochemically. So the third question, I think this is number 3. So the potassium permanganate solution is also known as Bayer's reagent. True or false? Other thing I forgot to mention that this I think we have already discussed this Karl Fisher reagent. If there is some oxidizing agent is there, because okay, like manganese oxide or zinc oxide, all these thing is there which can react with what is called iodine, and it can give color change also, and then extra Karl Fisher reagent will consume for that. So suppose for actually your water molecule is there 2 ml, and for 2 ml whatever amount of Karl Fisher reagent will consume, if you in your system manganese oxide is there, then extra amount of Karl Fisher reagent will consume to which is means we iodine, which are each means oxidize the manganese oxide, or no, so which are oxidize manganese oxide, oxidize the pyridine, and which can give you that means Karl Fisher reagent whatever amount that will be consumed. So as a result, whatever amount is should be there, more than that amount of Karl Fisher reagent will consume. So that value will be erroneous. Okay, so that I think, and we have discussed so many. I think Professor have discussed so many conditions, that what are the things if it is present in the system, like thiosulfate or stannous reagent or zinc oxide, which is a basic oxide. So if that thing is there, then there can be erroneous in the data. Okay, so the we can now concentrate on these problems. So the potassium permanganate solution is also known as Bayer's reagent. That is true or false? Can anyone tell? Okay, Ritambhara has written it is true. Yeah. So what is the Bayer's reagent? Can anyone tell? The answer is correct. What is Bayer's reagent? Which purpose we used to use? I think these things we have what is called, we have learned in BSc or school time. Bayer's reagent. So Bayer's reagent, what we used to, which purpose we used to use? Yeah, unsaturation test. Yeah, correct. So unsaturation test. So basically, if in your system you have the unsaturated molecule like ethylene, propylene, or something, so this Bayer's reagent, basically potassium permanganate, KMnO4. Suppose you have ethylene, let's say, which is an unsaturated alkane, and water. What used to happen? So this potassium permanganate, this is a what is called pink color solution, and this is ethylene. Okay, so if you add this thing, then what will happen? This unsaturated solution, it will form a hydroxyl group because it will oxidize to ethylene, and what it will form? So there OH is to form. Okay, and so this OH is to form, and this manganese oxide and K2MnO. So this manganese oxide, this is brown color it is. So earlier it was in pink color, and when you will add the what is called unsaturated compound or ethylene, that will form the brown color solution. Okay, and this is named ethylene glycol. Okay, so I think if I isometrize, I think this will be 2, because here 2 potassium ion is there, it will be 2, and for water it will be 2. Okay, so this is the main strategy. If you are testing some compound which has contained the unsaturated what is called reagent or unsaturated molecules, then you can get from there that Bayer's reagent you can use, and which will give that it is unsaturated means pink color, it will form brown color, so that will give the confirmation that your sample is contain unsaturated molecule. So basically all these things we are doing because when you have some sample or some pollutant and you want to know what are the element or which kind of compound is there in your pollutant, so that time people used to do all these tests, like where reagent they will add in small amount of your pollutant, and if there is a pink color it become what is called brown color, then they can tell that it is contain the unsaturated molecule, so that it answer is true. So the next question, the limiting current may be generated due to impurities in the electrolytic condition, so that is true or false? Limiting current, we have discussed these things. So what is limiting current, what is residual current? Which one will be the answer? Okay, I can discuss a little bit on what is limiting current. If you have plot I versus V, you are sweeping the potential like this. After that, you will get like this. This is the polarograph. Polarograph. Okay. So these things here. So due to that, and the why this is current, this current is coming due to the diffusion. By the which kind of current value is there? Current in the electrochemical system, 3 type of current is there. 3 type of current. What is 3 type of current? One is migration current. Two, diffusion current. 3, convection current. Okay, so for which purpose, which when we can observe this kind of current? So migration diffusion current, diffusion current due to the concentration gradient, which we have discussed earlier slide, due to concentration gradient. Okay, and migration current and convection current. Convection current basically you are doing some polarography, dropping mercury electrode and your electrolyte you have taken in the container. Okay, now you put one magnetic bead and you are stirring the solution, and during that time you are measuring the current. Okay, so due to the physical it is called disturbance, whatever current you are getting, that is migration current. So due to convection current, due to physical perturbation, whatever current is observed, so that is convection current. And migration current, what is to due to you are taking what is called in your electrolyte, you have the analyte, and in the analyte inside, when one atom is going from one place to another place through migration, due to movement of ion. Okay, so basically for that you use what is called supporting electrolyte. So we'll discuss more about this supporting electrolyte and analyte, all these things in future class. So when we will discuss cyclic voltammetry or linear sweep voltammetry, that time we will discuss more details all these things. Okay, for the time purpose I am telling these things. So this is the thing. So you have the supporting electrolyte you have, so you are getting this current, and after that this is you are getting a steady state thing. So this current, whatever, that is called residual current. And this, if you plot it up, this is limiting current. Also it is called that migration and diffusion current also. Okay, now suppose in your electrolyte some impurity is there, or suppose you have some Fe3 plus complex, so which is or Fe2 plus complex, which is oxidizing. So this is negative and this is positive. So negative to positive we are sweeping, so that means oxidation is happening. So oxidation is happening means Fe2 plus is going to Fe3 plus. Okay, now you are getting this current. Now suppose you have some what is called impurity is there. Suppose manganese is there, manganese 2 plus is there. So then in this potential range, if manganese also can give what is called oxidize, then suppose manganese going to manganese 3 plus, then it will give the current. Suppose it is like this, it is coming after manganese presence, it is coming like this. So this is due to the manganese and this is due to the iron. Okay, I think I can write a little bit. This is manganese, this is iron. Okay, so means due to the impurity also it is giving the current. So and this is the limiting current, and in this case here it is the limiting current. So in this case, this manganese, this is the impurity. So impurity also giving the current. So that means limiting current may be generated due to the impurity in the electrolytic condition. So that is true. Okay. So if in this region small hump or something is there in the residual region, then we cannot tell that that is coming this thing. So this thing is coming due to the supporting electrolyte. This is coming due to the supporting electrolyte. Okay, so this is the thing. So you can go to the next question. What is the next question? Combined glass pH electrode can be used as ion selective electrode for hydroxyl ion, potassium ions, sodium ions, any alkali and alkaline earth metals ion. Which one will be the answer? Okay. Ritambhara, I don't know, it is Ritambhara or something. Yeah, I think Ritambhara only. So CH, C is the answer. C has written. C means sodium ion only. So can you tell why sodium ion only? There is other ion also. Which things is required to make a ion selective what is called electrode? We have seen that glassy electrode which can be used as a pH meter, where hydroxyl H plus ion selectively passing. In pH meter, what is there? It is to like this, no? So here selective, this glass surface, this is selective for H plus. Okay, so that means this ion selective, that is depend on the size of the H plus ion. Okay, so this H plus ion and this sodium ion, that is almost similar in size. So hydroxy as H plus and OH minus, that is more larger in size compared to H plus. So this hydroxyl ion will not be, so that is confirmed. But potassium or any other alkali earth metal, that cannot be also possible. But potassium ion and sodium ion, that there is a probability. But we have to think that in sodium ion it's much smaller in size compared to potassium ion, and so H plus also smaller in size. So sodium ion can what is called migrate, or it can be used combined with glassy pH electrode, can be used as a ion selective electrode for sodium ions. Okay, and other things also we have seen that different type of composition, if you vary, then that can be selectively, that can be used for different what is called ion selective membrane, like electrode, basically ion selective electrode. So ion selective membrane is different thing, because there is some membrane, whatever you are using this glassy electrode, there is some membrane also there, like I can say that Nafion membrane, which is ion selective for H plus ion. Okay, so means membrane also there. This is the electrode, but this membrane also there, like Nafion membrane also there, and there is other different type of membrane is there. And for electrodes, ion selective electrode, we have seen that different composition of materials that can give a ion selective electrode for particular ion. Like I remember whatever this lithium oxide, if you mix 50% and alumina, that is 25%, and silica, that is if you mix 60%, then it will this whatever composition it will make, that will particularly ion selective, that is for lithium ion. Okay, so this composition will give for lithium ion ion selective electrode. Okay, so there is another example also we have observed. Okay, so the answer is C for sodium ion, where pH, glassy pH can be used as a ion selective electrode. Okay, so the next question we can see. So moisture content is detected by following acid base titration, complexometric titration, precipitation titration, Karl Fisher titration. Which one it will be? It is quite easy. Can anyone tell? Everyone should tell this question. This is quite easy. Yeah, all people are telling Karl Fisher titration. Yeah, we already discussed this thing. So moisture means water basically. So you have water molecule which can be detected. We have discussed the Karl Fisher titration, which can be observed by calorimetry as well as electrometry, electrochemically. Okay, so in Karl Fisher reagent, what is called Karl Fisher electrode, we use two parallel platinum electrode. So here it can give the current value. So we can go next question. Next question related to Karl Fisher only. Karl Fisher reaction, sulfur dioxide is used up in the formation of pyridine iodide complex, water pyridine complex, methanol pyridine sulfur dioxide complex, pyridine sulfur trioxide complex. Which one it will be? Hmm? This one also all people should tell. This is quite easy. We have discussed. Karl Fisher reaction, sulfur dioxide is used up in a formation. What it used to form? Yeah, Anil has written D, sulfur pyridine sulfur trioxide complex. Yeah, that is correct, because pyridine when is to pyridine plus iodine plus sulfur dioxide, what it is to form? Two molecule of pyridine NH plus iodine minus and pyridine or C5H5 we can write, then it will be more easier to understand. N plus SO2 O minus. So this is the sulfur trioxide and this is the pyridine. This is sulfur trioxide. Okay, so pyridine sulfur trioxide it is forming. So answer is D. Okay. Next question. In polarography, reduction of oxygen in alkaline condition can lead to generation of OH minus, H2O, water, hydrogen peroxide, H2O2, or OH radical. This is free radical. Which one will be the answer? Oxygen reduction. Can anyone tell? Oxygen reduction reaction. So this is quite interesting field now. Means it is progressive field. Basically, so many people are working on this thing, oxygen reduction reaction. What we can tell people short form it is still ORR, oxygen evolution reaction. People tell OER. Okay, so people used to tell this thing. I think means if you people aware okay, about research that in energy storage system. So now okay, whatever lithium ion battery which is commercially available, but Now fuel cell, or if you say that metal air battery, one of the promising candidate for higher energy density key component. Metal air battery, I can say air battery, where this ORR and OER is to happen. So basically, if you if you heard that zinc air battery or lithium air battery also is there. So this thing, if I don't know, in the battery metrology section, one particular week is there. So in that section, which topic we will discuss, but this things is there, which is quite advanced. Means if you see this lithium air battery, where this ORR and OER, oxygen reduction reaction and oxygen evolution reaction, zinc air or metal air battery, basically this thing is to happen. And this in particular lithium air battery, this whatever capacity of lithium ion battery, this is 10 times higher, 10 times higher or whatever capacity of lithium air battery, that 10 times higher capacity. So that means if you practically if you see, means although this lithium air battery is not commercialized yet, but if it is commercialized, then it is to happen like this, that in lithium ion battery, suppose it is running in your cell phone for 1 hour, then for lithium air battery it will run for 10 hours. Okay, so in it will be like huge capacity. And in electric vehicle and all this thing, it will be highly it is called, it will be highly progressive. So that is there. So we can come to the question that oxygen reduction reaction. So oxygen in alkali condition, what it will be form when oxygen is reduced. So basically in alkali condition, oxygen it will go to OH minus, because in your solution OH minus is there. So when oxygen reduction is happening, O2 is going to OH minus, and in the oxygen evolution reaction, what is to happen? OH minus, it is to go O2 plus water. Okay, so this is the ORR, oxygen reduction reaction, and this is the OER. Okay, so this is not a balance equation, but this thing is to happen. So the simple question. So which one will be the answer? A is the answer. Okay, OH minus it is to form when the oxygen will reduce. Okay, and this ORR, OER catalysis part people used to do when they are developing different kind of metal oxide or organometallic complex. Nowadays, organic molecule also people use as a catalyst for ORR, OER. Okay, and in non-aqueous system also people use organometallic complex and organic molecule as a catalyst. Okay, so I am not going to that details. That these things are there. Okay, so we can go to the next question. The determination of dissolved oxygen can be carried out successfully by polarography. Yes or no? How much dissolved oxygen is there that can be measured by polarography? Hmm? What will be the answer? Yes or no? Dissolved oxygen. True. Yeah, true means it can be dissolved oxygen, because what is called oxygen, suppose it is reducing to what is called OH minus, reduction current is happening, or then what will observe a current value. So suppose this is positive and this is negative, then it will get like this polarography. If you do these things you will get, and we'll know the Ilkovich equation, d Ilkovich equation. What is D-Ilkovich equation? ID diffusion current, that is equal to 607 N C d to the power half M 2 by 3 T to the power O. 3 by 2 T to the power 1 by 6. So this is the Ilkovich equation. Okay. So in this 603, so here all these Faraday constant, all these things are there. So after this thing, this is in for room temperature. Okay. So this equation is there. That means you are getting from here this diffusion current ID. So ID you know, and number of for O2 is going to O is minus. What is the reduction? It is 4 electron process. Okay. So if it is 4 electron process, then N is equal to 4, and C concentration you have to calculate. Okay. And M, what is the mass of dropping mercury? And T is the time for falling the drop. So that things we know. Okay, so that means all the parameter you know. Diffusion is the it is called diffusion of oxygen. So that also you can get from the literature. In water molecule diffusion of oxygen, it is available. So all the parameter you know, then you can get to know how much oxygen is dissolved in the solution. Okay, so that means electrochemically or polarography can give the information of the dissolved oxygen, how much oxygen is dissolved in the solution. Okay, so we can go to the next question. So pilot ion method is suitable in polarography because it accounts for, I think this question I think repeatedly we are discussing. So these things is there. So what will be the answer? Pilot ion method. Okay, I can do. I think it is B. So I think this question we have discussed lots of time. Okay. Now we can discuss some of the numerical problem. So determine the diffusion current of nickel solution. If diffusion coefficient of for nickel having concentration of 3 millimolar is 0.69 into 10 to the power minus 5 semi square second square. This is the diffusion coefficient. Then flow rate of mercury is 3 mg, and drop time it is given. So what is the diffusion current? So which equation we have to use from this? Can anyone tell how we can proceed with this problem? It is quite easy. Ilkovich equation. You can write Ilkovich equation. What is Ilkovich equation? Ilkovich equation ID is equal to 607 N d to the power half M 2 by 3 t to the power 1 by 6 C. C is the concentration. Okay, so what are the information is given, we can write here. So what are the C? It is given C is 3 millimolar. Okay, and D diffusion coefficient is given 0.69 into 10 to the minus 5 centimeter square second inverse. So this centimeter square second inverse, this is the heterogeneous diffusion, means diffusion coefficient in the solution. Okay, and what other things is there? AM is there. 4 mg second inverse, t is 4 second it is given. Okay, so what is nickel solution? So when nickel solution is there, so what will be the reaction? Nickel 2 plus, it is 2 electron reaction, so what it will form? Nickel 2, nickel not. Then what is the n value? N is equal to 2. Then you can put in the equation all the value. So the current value, what will be? It will come in microampere. I think in the class also we have discussed. It will be in microampere. So ID you can write 607 N2 diffusion coefficient 0.69 into 10 to the power minus 5. Okay, to the power half into AM is 4 mg per second, 2 by 3, and T, what is the T value? 4 second, 1 by 6, and concentration 3 molar. Okay, so this one anyone can calculate what is the value. People can also calculate how. 0.69 10 to the minus 5 half. How much this will be? 4 means 16. 16 1 by 3, 4 into the power 6 into 3. I think I need the calculator, because without calculator I think this thing cannot be calculate. If people can calculate this one, how, what is the answer is coming? 1214. Can anyone tell?
Fourteen milliampere.
How much it is coming? You can write in the chat box. I am also calculating. Divided by 2. Okay. So mine is coming 31.57 microampere. Okay. So people also can calculate how it is, how much it is coming. So you can go next problem. So in polarographic estimation of cadmium 2 plus ions, the following results are obtained. ID value, diffusion current is obtained 5.65 microampere. Diffusion value it is given, mass also given, T also given. Calculate the concentration of cadmium 2 plus ion in the sample solution. So it is same what is called Alkovich equation. So ID is equal to G607 NC d to the power half m to the power 2 by 3 t to the power 1 by 6 So I have to calculate C, concentration of K sample. So what I can write, C is equal to ID divided by 607 N D to the power half M to the power 2 by 3 D 1 by 6. Okay, so I can put all the value. D diffusion current 5.65, it is given 607. N cadmium 2 plus, it is 2 electron it will accept, what will form cadmium not. So N is equal to 2. So N is equal to 2, 6.85 into 10 to the minus 6 half. AM is 3.45, 2 by 3, 2.90, 1 by 6. So how much it will be? So this is quite easy, means this kind of question also it is to come. Okay, from whatever value means given, so you have to think that which equation you have to apply. Means when they are telling polarographic, you have to remember that only Alkovich equation is there to calculate the diffusion current. So now you have to what is called think that what are the information they have given and what are the it is called what we have to calculate. So before doing that thing, so I want to draw attention is that this equation unit you have to remember. So diffusion semi square second inverse and am it is called weight in mg per second and time is second. So that time the current value is coming in microampere. So if because we have put all these value Faraday constant all these things and our temperature at least in 607. Okay, so always all these things, this is our CGS unit, so these things you have to remember. So which if it is in other unit, then you have to convert in this unit, then you will get the current value in microampere. Or if the current value you are getting in milliampere or ampere, then you have to convert in microampere, then you will get the right answer. Otherwise sometimes it will not means actually in physical chemistry this is a very important thing that unit balance is a very important thing. So sometimes you have to change the unit and all the unit you have to put in the same uh, unit, like it is in SI unit or it is in CGS unit. So that things you have to keep in mind. Okay, so anyone has calculated this thing? 602 607 into 2 6.25 into 10 to the power minus 6 minus 6 half 3.45 2 by 3 2.9. Okay, total value 5.65 divided by answer. Okay, so mine is coming 0.64 19 millimolar. Okay, so this one is my incoming. Okay, Anil is getting 20 millimolar.
Sir, I forgot to divide it with
divide
5.5.
uh-huh. Okay, if you divide it, then you will get this thing, I hope. Okay, so next question you can so a 5 millimolar solution of cadmium ion gave the diffusion current of 40 microampere at constant temperature. Find the diffusion coefficient of cadmium ion. So given that rate of flow of mercury m is given, these things, and drop time also given, so it is same thing only. So I can just write all these things. id is equal to 607 n d to the power half m 2 by 3 t to the power 6 into c. So I have to calculate this d. So d to the power half, I can write id 607 n not d m 2 by 3 t 6 and c. So now d is equal to id 607 n m 2 by 3 t 1 by 6 c square. Now I can put all the value. 40 607 into n will be 2, because cadmium 2 plus 2 electron, it will go cadmium not. So it will be 2. am is 3.2, 2 by 3, drop time t 2.2, 1 by 6, and concentration is 5 millimolar, and that will be square. Okay. Okay, so this is how much, what will be the value? So this one is coming 2.6613 into 10 to the minus 3 into whole square. So it will be 7.08 10 to the minus 6. So diffusion is semi-square second inverse. Okay. So you people can individually, you people can calculate, and this answer is coming or not, you can check. Maybe I am also doing wrong, but you can check once. Means this is the procedure. So in the means all the value is there. So during the calculation in calculator, maybe there will be some mistake, but I think it is correct maybe. Okay, so this is the thing. I think yeah, this is the homework for you people. So the diffusion coefficient of titanium plus is 2 into 10 to the power minus 5 centimeter square. So and the for and okay, for cadmium 2 plus it is this. So both this is a mixture of two ion. So one is titanium plus, other one is cadmium 2 plus. Okay, so both have given the it is called diffusion coefficient. Now if a 1 molar solution of cadmium 2 plus 5 gives, I think it will be gives, so gives a diffusion current of 8.15 micrometer. What will be the diffusion current of 1 molar of titanium 2 plus using the same polarographic cell? Okay, so if people can do this homework. So both have given the diffusion coefficient. Now I can give some hints that you have to think that this one is one electron process, one thing. This will be a two electron process. And other thing it is given. So I think it won't be a so much what is called difficult. So I think you have to calculate for both things, as it is a same polarographic cell. So you are measuring in the same what is called polarographic cell, though all the cell constant, all this thing will be same. Okay, so that means you can do the ratio of two different current. One current it is given, so other current you have to calculate. Okay, so these things you people can do, and you can I can give the answer for this. So answer will be 6.79 microampere. So if people can calculate, and it can you can match with this. Okay, so next question we can discuss. In a polarographic titration, calculate the concentration of 50 ml of iron solution, which is showing 10 microliter of microampere of current. In the same cell, 20 microampere is the diffusion current after 25 ml of standard solution of iron solution, which concentration is 25 millimolar is added. Okay, so we have to calculate the concentration. So this is basically, I think we have discussed these things, what is called this method of standard addition method. I think we have discussed. So with that thing we have to calculate. Okay, so basically if I it is called sorted that discussion, then it will be more clear. Okay, so basically we have observed that suppose you have a polarographic curve, that is E and it is I. So what it is telling, that you have a curve and you are getting like this. Okay, and your current you are getting, this is the diffusion current ID1, and after adding another sample you are getting, this is current, this is ID2. Okay, so now question is, what is the concentration? Suppose this is the standard solution, this is for standard solution, and here also same compound, here iron also it is given, iron also it is given. So means in the initial state you are doing for standard sample, after that some unknown concentration you have added and you are getting this current. Okay, so then they are asking them what is the concentration of this unknown component. Okay, so that is the thing. So what we have learned, that suppose you have current I, suppose for this one, this is I1. We know the I1 is equal to K. This is the what is called diffusion current K, and concentration C is the unknown concentration. And other case you have you are getting K I2, this I2, that is K, how much volume we have added, so depend on that. So V into unknown solution concentration, VCU plus V volume of the standard solution, concentration of standard solution, and divided by total volume. V, I can write V1, this is a V1, I can write, this is V2, and this is V2, V1. Okay, like that. Then we can, if you, okay, what is called, we have to calculate what is this CU, this thing. Then what we can do, we can calculate this here also K, here also K. So I can write K value, that is I2 V2 plus V1 divided by V1 Cu plus V2 Cs. Okay, so I2 here, you know the K value, this thing, so I1 by C, so I can put this one, I think next slide I can write. So this one K I1 by Cu, I1 by Cu is equal to I2 V plus V, V2 plus V1 by V1 Cu, V1 Cu plus V2 Cs. Okay, so if you calculate this thing, then we I1 I2 Cu V2 plus I2 Cu V1, I can write here this one and this one, I can multiply I1 V1 Cu plus I1 V2 Cs. So what it will be, Cu we have to calculate, so C, all Cu you can take in one, Cu I2 V2 plus C I2 V1, and this one it will come this side, I1 V1 is equal to I1 V2 Cs. Okay, so Cu is equal to I1 V2 Cs divided by, here this one V1 we can take common, so I2 V2 plus V I2 minus I1 V. Okay, V2. No, this will be V1 and this is V2. So now I think all the parameter we got. So these things we have to calculate, and all the things I can write here. So this is given that calculate the concentration 50 ml of Fe solution. So means V1 it is given 50 ml. I can write in another color. It will be. So V1 it is given, V2 it is given how much? Standard solution 25 ml, and then current value for calculate the concentration, unknown solution I1 it is given 10 microampere, and same cell 20 diffusion current, standard solution I2 it is given 20 microampere. Okay, and CS it is given 25 milliampere. So what will be the answer? So all the parameter it is given, so we have to calculate the CU here. Okay, so I can put that value. I think if people can do this thing, this value you will put, so you will get the answer. So what is, I think that's all. Thank you all. I think other things we have discussed in the pilot ion method, wave height concentration that we just discussed, and all other things. I think we have discussed half wave potential. Basically, means where your this is means this is called whatever potential. This is the half wave potential of this redox process. So your residual, suppose this is residual current, here diffusion current, and in between whatever this is the half wave potential. Okay, so that things also we have discussed. I think almost all the problem we have discussed, and all other things also what is called in this week whatever professor have discussed. So that things also we have just recalled it. And if anyone has any question or any inquiry, you people can ask. And this homework also you people can check once. So I'll share this question PPT. So you people can check once. Anyone has any question? Okay, so if anyone don't have any question, then I think we can conclude the class. So if anyone has any doubt, you can tell. So, Anil, so your problem is sorted out?
Yes, sir. Actually, in the Swayam portal, and that
Mm-hmm.
whatever the assignment solutions is there now, so
Mm-hmm.
still that is it is not opening whatever the link provided in the Swayam portal.
Mm-hmm.
So that's why I mailed you, but afterwards you have sent me. Definitely, I will. I am appreciating that one actually. But if this is if the same thing is continuous, it will be difficult to each and every week. I need to ask you, sir, actually
Oh, okay, okay.
to send the PDF file because whatever I sent the link, a file, C drive, something it is there.
Mm-hmm.
Each and every, the same week it is they are giving the same link, but when
Mm-hmm.
I opening that link, it is not opening the PDF file. So this
Okay,
becomes
okay.
this is the
Just
it is in the Swayam portal. It is in the Swayam portal actually.
okay, okay. Actually, okay. I just a minute. Anil. Because you have okay CHP down assignment. Yeah, actually this link no, that is not my link. Okay,
Okay.
means yeah. So this is means whatever I am sending to them. So
Mhm.
their record means they are download that thing. Sorry, they have
Okay.
download that thing. Then they are uploading in their portal, and that
Okay.
link I think they are sharing to you. Okay, so
Yes, yes.
I think you can ask them to give the access for that.
Access. Okay.
Because if you ask that I have, you can add the email ID, which
Mm-hmm.
email ID you want to get the access. So if you
Mm-hmm.
ask them to get the access of that, email ID. You can attach the email ID, so you can send the mail. So they will give the access for that email ID.
So to which email ID I need to send the
Means
query?
if you what is called assign the this course, whatever
Mhm.
email ID you have used, so with that email ID you can share.
Okay, sure, sure, sure. Okay.
Okay. Otherwise, if you are not getting, then you can just put a message to me. Okay,
Hmm.
I'll share the PDF and all
Uh,
other thing. Okay.
Okay, I think I can directly ask you, but each and every week, if I'm asking you, I think you also feel bad and all those things. So therefore, I stopped that one because only the first 2 weeks I can download, but the third week and the fourth week I am unable to download it. Mm.
Oh, okay, okay. Then fourth and third week, I'll share the thing. Okay. I think I have shared the what it's called third or fourth week assignment, previous year assignment. I think PDF
Yes, yes,
copy.
yes, yes. Yeah, yeah, you are
So
sure. Yeah.
so other things I'll share with you. No issue. Okay.
And one more thing is, sir, in the examination, it will
Mhm.
be like an MCQ questions, or we need to.
I think it is written in the if you see the whatever course in the past lecture, maybe week one or more before that introduction class. So
Okay,
there it is given that means how much contribution from the assignment, how much contribution from the half yearly, or how much from the
and the
last exam.
contribution,
And
and the
and
contribution,
it no, no. When you
contribution.
will assign, it is called when you will go for register the for examination. So in
Hmm.
that portal, how is the it is called question pattern? It is written there. So
Okay,
I
okay.
exactly forgot there something because I also read that thing, but I forgot exactly how is the pattern. I think MCQ also there. I think some. Most of the thing are MCQ, I think, and
Yeah,
multiple answer
choice.
type also.
Hmm.
MSQ also it is there, I think. So you just when you will assign means register for exam, so it that side only it is given.
Sure. Okay, okay. I will go through that. I will go through that.
Mhm.
Okay.
Okay.
Thank you very much.
Okay.
Thank you very much.
Okay. Thank you. Bye. Okay.
Bye.
Okay.
Good
Thank
night.
you all.
Good
Have
night,
a
sir.
good day.
Yes, sir.